Thanks a lot for inviting me today and for coming. It's great to be here and see so many people interested in databases. Today I kind of just wanted to put together a talk that would be as useful for as many people as possible, covering lots of different types of performance problems that we've had. Most of them are generalizable to other databases, but we're talking about Cockroach specifically today. And how we solve those. Some of them are pretty basic. Most people here probably already know about it. If you're new, you might not. Others are more niche cases. So hopefully everyone gets something out of this. So first, I wanted to talk a little bit about what makes sports betting workloads a little bit different from other workloads I've seen. Probably the most interesting thing is they're very bursty, but you can tell when the bursts are going to happen. Usually you have a continual drip of data from information about sports events coming in. Then you have a spikier trickle of people placing bets on those events. But the big tsunami comes when it's time to settle the bets, which is usually when the sporting event ends. So yeah, but most of the time you have a pretty good idea of when that's going to happen. You can predict when you need to scale up and scale down. And then another interesting thing is you tend to have very geographically distributed workloads, customers in variety of places, and you have lots of regulation and data domiciling requirements. So for example, we're regulated by the Federal Wire Act, but there are also gaming authorities at the state level that implement different requirements, and sometimes they're local or tribal regulations as well. So it gets pretty complicated. Sometimes it's almost kind of like GDPR, but if every country in the EU implemented GDPR differently, there's a lot of compliance and limitations on where we can place what data, and those big tsunamis of settlement activity are very write heavy. Update heavy specifically for most use cases. So we started out with some software that was originally made for a more traditional database system, and we sort of had to learn how to adapt that to work with a distributed database. And some of this seems kind of obvious, but we had to think about how to get our heads around what's different here, mainly in terms of performance. So like things you think about when you're tuning a traditional database, you might think about your query design, what hardware you're using, what sort of configuration options there are in your DBMS, what sort of transformations the optimizer is capable of a distributed database. It's kind of all the same stuff, but you have to think a lot more about data placement is what we learned. So if you're moving lots of data across the continent, it doesn't matter how well written your query is, or how efficient your query plan is. It's probably just going to be slow, not just due to how TCP works and speed of light issues. In addition to having a good query tuner on hand, it's been really important for us. We have a fairly large self-hosted cluster distributed around the country. And we've definitely benefited a lot from having really good networking people who know things like BGP well. And that's something I hadn't really encountered with databases before. We rely much more on networking people than we have other places I've worked. Another interesting thing about distributed databases is, so in Cockroach you can change almost anything online with zero downtime, which is amazing. But what I started to realize early on is that once you run that alter table command and it returns, you're not really done, because with a distributed system, there's lots of more work that has to happen in the background, like replication, range splits, and merges, leaseholder changes. So we started to learn, make a change, monitor CPU usage, back off. When CPU usage comes down a little bit, and then you can make more changes. Originally, we were trying to make lots of changes in a small window, and we kind of overwhelmed the cluster unnecessarily and had caused lots of knock-on issues. So that's all avoidable. With a distributed system like this, we have to think a lot more about data placement and techniques for moving data closer to the clients. So one of those techniques we used was list partitioning. was really effective in allowing us to pin certain types of data to certain localities. The downside of list partitioning is you do have to rewrite queries in some cases to make sure you're using your partition key in all the queries, and that makes writing the queries more complex and also planning the queries more complex. And we did have some issues with quite high planning time on some queries that was sort of exacerbated by the fact that we have some really wide tables. That last point there about the check constraint, that can help quite a bit with performance and partition queries. And that's just one option for pinning data to certain localities in Cockroach. There's also regional tables and a number of related things. And I think I haven't used those much, but there are some good in-depth talks about those coming up, I believe. Not for me, though. Another data placement related technique we've used a lot, most of you have probably heard of, is follower reads. So at some point, working with a database that runs under a serializable isolation level, you'll probably wish that you could relax the isolation level and just give me some anomalies. Yeah, I'm not worried about it. Just let the query run. You can't do that in Cockroach, which is fine because there's something else you can do. If you don't need the latest data, you can specify that you want the data to be consistent only as of some time in the past when writes are no longer being accepted. And that pairs really well with another feature called non-voting replicas that most of you have probably heard of. So you can use the non-voting replica to get consistent reads as of some point in time in the past from a replica that's very close to your client. So here's some examples here where we're running a query without follower reads from a remote site. It takes 130 milliseconds. We add follower reads to it. It takes a couple milliseconds, and that's just because the gateway node that client is talking to doesn't have to go talk to the leaseholder at another site anymore. So that was a big win for us in cases where we don't need the latest data. There are some cases where that could be really dangerous, like looking at account balances and stuff like that. But for others, it works pretty well. Another data placement related topic is how many ranges do you want? Well, the default settings for the range size actually work really well in a lot of cases. I've probably caused more problems than I've solved by trying to change those. And a good range count is usually, you want enough ranges to keep your nodes, to distribute your load across your cluster nodes, but you don't want too many because each of those ranges does have a little bit of overhead. So on this graph here, there is an experiment I did. That first big spike is where I configured a table to have about 10,000 ranges instead of 100. And you can see CPU usage shot up. There was lots of activity splitting and merging the ranges. And then it settled down, but it settled down to a point a lot higher than it was before. And then that spike continued until I set the range count back. And this is on a system without much activity. So that increase in CPU usage was probably just from adding lots of ranges. And that's kind of an extreme case. Most of the time, no one would want tens of thousands of ranges, but some people will, or accidentally at least, and it illustrates a point. So when we started trying to get this to perform well, the first thing we wanted to look at was really easy stuff to find. So one of the ways to find really easily detectable performance problems in Cockroach is to look at the output of show full table scans, and that will basically just show you any query that's reading the entire table. Now that's not necessarily a problem. You might, if you're returning the whole table to the client, you probably need to read the whole table. So table scans aren't always bad. Sometimes they're the most efficient way to run a query. But if you're reading the whole table and returning one row, then yeah, you just need an index, most likely. So this has been really helpful. A somewhat better metric might be trying to find queries that have a really high ratio of rows read to rows actually returned to the client. Although that can be okay too, like queries that do aggregations and things like that. And then in the latest version, 22.1, we also get index recommendations. I haven't seen a lot of recommendations from that I wanted to actually implement yet, but most of our queries are kind of tuned to death at this point. And if it was more like Greenfield, we'd probably see more useful recommendations. I've heard that the types of recommendations the explain plans are capable of recommending now are pretty sophisticated. So another thing we realized was that having a good indexing strategy isn't just about getting a fast query. It's also about avoiding concurrency problems. So if you're reading lots of data unnecessarily and you're trying to update that data at the same time, you're probably going to get retries and errors like that one you see there. So you do have to be a little careful about how much you read and what you read. That's just life with serializable isolation, which makes things a little more difficult, but also has some great benefits. So once we started looking at lots of our queries, we realized we had lots of issues with predicate pushdown due to our index design. So this query plan here, initially it doesn't look that bad. It's reading data from an index, it's returning it to the client. Maybe that's fine. But what's actually happening is it's reading 8,500 rows out of an index, and none of those actually match the query. So it's doing a lot of reading, and then the query is basically a no-op. So with a better index, you could get rid of that filter operator, push all the predicates down into the index read, and then you'd have a much faster query. When I was looking at that type of issue, I got some advice that was relayed to me from support, originally from someone on the SQL queries team. I don't know who this quote is actually from, but it really helped me think more clearly about how to create indexes in CockroachDB. So yeah, the slides will be distributed later, so you don't have to read through all this now. But basically what it's saying is if you have a predicate that has a search conditions on a number of different columns, any number of those can be equality conditions, and you'll get an efficient search. And then only one of those can be a range condition. And the equality conditions need to be on the left of the index declaration. And if you fulfill those requirements, you can avoid doing lots of unnecessary reading, and you can avoid having that filter operator in your query plans. So here's an example of what I mean by equality and inequality predicates. So things like that, like equals in are equalities. You want the columns that are searched on those conditions usually in the left of your index declaration. And then the inequalities are things like greater than, less than, is not null, not equals. And you'd usually want those on the right side of a multi-column index. So here's an example this is I think this is actually the same query we looked at a few slides ago, but now you can see that we've changed the index definition so that the columns with equality filters on them are in the left side, and the one that the date column that we're doing a range search on is on the right side. And now we get a much more efficient plan. We'd basically just do an index seek, and the query is a no-op because nothing matches this. So that's much faster. But then you can run into some tricky situations, like how do you still get an efficient index read if you have multiple inequality predicates? Like if you have greater than a date and some other column is not null. Well, partial indexes are a great fit for that. You can declare a predicate as part of the index definition. So this is another thing that's been really helpful for us. I think the slide is actually wrong. I wrote that there are no statistics on partial indexes. I think it's more true that there are some limitations on what statistics are gathered for partial indexes. But that can affect what indexes the query planner chooses. And in some cases, you might get an inconsistent usage of the partial index, or the optimizer might not choose to use it when you correctly think that it should. So yeah, you can work around that with index hints. Sometimes it's really easy to get someone to add an index hint. Sometimes it's not. But yeah, at least the way things are written now, to get a partial index used consistently, sometimes you may need to add an index hint. And another interesting thing, I don't have time to elaborate on this much, but sometimes you might need to include a column in the partial index definition, even though it's already known from the partial index definition, even though its value is already known from the partial index definition. So you may see some cases where you have a partial index predicate and like where foo equals something, and the query already knows that, but nonetheless you might see it retrieve the value of foo from the primary index. But if you store that column along with the partial index, then that won't happen. And I'm not sure if there's an active GitHub item for that. It might be something that's being worked on. Now, what if you have or predicates? This is where it gets tricky, because yeah, how do you search a B tree efficiently for an or condition? Well, one way to handle that is to create multiple indexes. And this is a cool transformation. Some other databases that have been around a lot longer can't do this, as far as I know. But the optimizer can basically rewrite that query as a union of reads from each of those indexes. And then even though you have or predicates, you can still avoid having the filter operator in your query planning and get a fast query. There are some cases where you can actually get a better query plan by rewriting that query explicitly as a union all. The main case for that is if you know that you won't have duplicates, or you don't care that you have duplicates in your result set, you can get rid of a distinct operator that you usually get from this transformation just by rewriting the query as a union all. So here's kind of an example of what that transformation looks like. And you can see the distinct operators up there at the top filtering out the duplicates. And then with the explicit rewrite as an actual union all, you can get rid of that if you don't need it. Obviously, if you don't want duplicates, then you might need it. But yeah, that impressed me, and it was good news for me when I learned about that. So another thing we've looked at a lot is hash sharded indexes. This is a cool feature. Basically, it lets you add a computed column. It used to be a stored column. Now in the latest version, it's a computed column that computes a hash bucket ID and returns the hash bucket ID. And that gets added to your index definition. So that's really good at distributing sequential data, like an ascending ID or a date across different ranges. But that's kind of the only thing it's good for. It's just designed to solve that one use case. And some people, including us at one point, kind of went crazy and just did this everywhere. And that's probably not the best idea. Just because hash sharded indexes do slow certain types of reads down, mainly range scans. Not as much as they used to on version 22, but still some. So I would just say don't use this unless you actually have this problem. And you also make sure you look at your alternatives. So that in 22, there's the new unordered unique row ID function. And that helps you avoid that ascending key problem without having to go to giant, ugly UUIDs. So I just barely got through that in time. This is all just scratching the surface. A lot of this stuff we could probably talk about for days. But I wanted to just get as much info out there as possible as quickly as I could. And main takeaway for me is Cockroach is very flexible. Don't despair, don't give up. If you have a problem, there's almost certainly a solution for it. But experiment, test carefully, try to use a realistic workload if you can. Don't take my word for anything, test carefully. And if someone at Cockroach Labs says I'm wrong about something in this presentation, they're probably right and I'm probably wrong. But, but yeah, thanks a lot for inviting me. I'm really glad to be here. I hope that benefited you. Thank you.